Alrighty, so we are now recording. So thank you once again for being here for the CHEM223A infrared spectroscopy lecture, where we are going to talk about infrared light and how we use it to determine the functional groups of our organic molecules. That was probably one of your pre-lab questions, right? What does IR tell us? IR will tell us the functional groups in a molecule. Have you guys began talking about functional groups in your lectures? Just yes or no? We're halfway through, so you should be already talking about it. So the functional groups are the parts of the molecule that react, right? Let's see, I have some people in the chat saying yes. Yeah, definitely. If you haven't yet, now's a good time to get started, right? So even though in chemistry we talk about molecules and molecules can react, sometimes it's not the whole molecule that's reacting, it's only part of the molecule, right? You can think about it in terms of a car, right? Sometimes the wheels of the car are the ones doing the moving, not the car itself, right? So only certain parts of the molecule participate in chemical reactions. And when we're doing organic synthesis, which we do in organic chemistry, you actually create molecules and you need to find out whether you are on the right path or not. And so we cannot go down to microscopic size and actually see the atoms. We have to measure them in different ways. We can do melting point, we can do TLC, we can do column chromatography, and this is just another thing that we can do as well. And usually we do it pretty often in organic synthesis. It's infrared spectroscopy. So let's talk about spectroscopy first. Spectroscopy. Everything you see around you right now, if you look around you, you can see something, I hope, right? And even if you can't see all the colors of the rainbow, even if you are colorblind, you should still be able to see something. And this is because light travels in the form of a photon, and this photon is part of what we call the electromagnetic force. There are four fundamental forces in the universe. Gravity is one of them, electromagnetism is another one, and then we have, of course, the strong nuclear force and the weak nuclear force, which you can learn about in upper division physics if you're interested. But the one that we interact with most frequently on a daily basis is the electromagnetic spectrum. And out of the entire range of the electromagnetic spectrum, we only see a small portion of it called visible light, right? Of course, it's visible. We see it. And if you've ever seen a rainbow outside after it rains, all of those colors are visible light. So everything that we see, the trees, the sky, our vehicles, the roads, a nice colorful compound, everything that we detect is in the range of visible light. We have built-in spectrometers in our bodies. We call them eyeballs, right? So it's not the entirety of the electromagnetic spectrum. There's a lot more that we just don't see. And so, for example, if you've ever learned the colors of the rainbow in middle school or maybe in high school, you might have remembered the acronym Roy G. Viv. Roy G. Viv. It stands for the colors red, orange, yellow, green, blue, indigo, and violet. With red being the one that has the lowest energy and the longest wavelength, and violet being the one that has the highest energy and the smallest wavelength. And if you remember, perhaps from physics or perhaps from a documentary or some shorts you might have seen on the internet here and there, you might remember that a wave, well, it looks like a wave, right? Let me try doing my annotations here. A wave looks like a wave, and it has a wavelength. So usually we say from this point to this point, and we say that it's one wavelength, lambda. And then the size of the wavelength and the energy of the wave, there's a relationship between them. So let's think about it for a little bit. So like I mentioned, red has the longest wavelength of visible light. And then a little bit below red with a longer wavelength and lower energy is infrared radiation, which is what we're going to be talking about. And you can't see infrared radiation, but you can definitely detect its interactions. So if you've ever been at a campfire at the beach or in the forest at night and the fire is burning right in front of you, you can feel the infrared radiation hitting your body. We detect that as heat because infrared radiation vibrates the molecules in our bodies, and that vibration is picked up by our nervous system as heat. So even though our eyeballs cannot detect infrared radiation, we still have a means to indirectly know that it's there. If you've ever been to some really cool like monster truck shows or Universal Studios where they have explosions, you will usually see the explosion and you can feel the heat even though it's very far away. You're not feeling the heat, you're feeling the infrared photons traveling and hitting you. So again, we can't see it with our eyes, but we can definitely feel them. And then even lower energy and longer wavelength than infrared radiation are microwaves. Microwaves because usually they're starting from micrometers to about meters. And these are the ones that we use at home. So fun fact, this was discovered by some guy in the military working in the 1940s. He was working on the device that generates the microwaves, and he had a chocolate bar in his pocket. And then he realized that every time he turned on the machine, the chocolate bar was melting a little bit more. And so he correctly concluded this must be emitting some sort of radiation that is causing the chocolate bar to melt. Well, the chocolate bar's in his pocket. I'm sure he was probably worried about other stuff as well, burning up or heating up. But he was a scientist, so he noticed the chocolate and he realized he could probably do something with this. And after much development and commercialization and capitalism, we came up with the microwave oven. And now all of you have experience using microwaves to heat up your food. I hope you do, right? I hope we've all used microwave ovens. And the thing is, the microwaves actually vibrate the water molecules and rotate them as well. And that friction is what heats up your food. That motion is what heats up your food. If you've ever rubbed your hands together and they get warm after a while, well, the molecules do the same thing when they interact with matter rotationally or vibrationally. Sometimes there can be some sort of heat friction. And that's how microwaves work. And that is why not everything gets heated up by microwaves. And that is why sometimes some parts of your food get heated up better than others, simply because the water content is much better than the rest of the food plate. So just again, we do use all of these waves in everyday life. We interact with them even though we can't see them. And we also used to use radio waves. I mean, I'm not sure if you guys listen to the radio anymore, but definitely I grew up listening to the radio. I was lucky enough that I was still able to record things on a cassette. Like the cassette player was built into the radio, and you have to wait for your favorite song to come on, and then you press record and you record the whole thing, and then you press stop when it ends. Try not to get the commercials in there. But anyway, we used to listen to the radio a lot more. And even if you don't, you're still using radio waves right now because Wi-Fi, wireless fidelity, Wi-Fi is using radio waves. So your room is full of radio waves right now. And if you're on the, conspiracy part of the internet, you may have read recently that they can use radio waves in the Wi-Fi to find out where you are in the room. And that's because the waves will hit you and they will reflect and they will go back to the modem and you can measure the differences and see what objects are taking up space in the room. So yes, we are using radio waves right now in the form of Wi-Fi. And if you've been in the UV room and you looked at that big instrument in the back, that is an NMR spectrometer, which you will learn about next semester, nuclear magnetic resonance. We shoot radio waves in a very strong magnetic field at some compound, and we can find out how many hydrogen atoms it contains very precisely. It's magical almost. And so these have the lowest energy because they have the longest wavelength. So you can just think of the wave as, very long, very large. Some of these waves for radio waves are kilometers. And this is why Wi-Fi has a good range because we're using long wavelength electromagnetic radiation. And this is why AM radio can travel for hundreds of miles without being interrupted as well. So yeah, these are some of the examples of the electromagnetic radiation that we have and how we use them. And on the opposite end, we have ultraviolet light, which you're also very familiar with at CSU Long Beach, right? You guys will get sunburned if you're standing outside in the sun for too long. And that shows you how much more energy ultraviolet light has. Ultraviolet light will have a smaller wavelength, but a lot more energy. You will get cooked, literally, if you stand outside too long in the sun. Your skin will turn red, it will blister. You can get first or second degree burns, or maybe third. I'm not exactly sure with my terminology which one is the most severe one, but it can be bad. It can be bad. Ultraviolet light is powerful. Some of you may even do it on purpose. You go to tanning salons and get burnt, right? The point is, ultraviolet light has a lot more energy than violet, ultraviolet, beyond violet. And even more intense are X-rays, which we also have experience with at the dentist, at the doctor. Some of you will be working with X-rays in the future for your careers. This is very high energy radiation. You have to be careful. That's why you have people, your patients, wear the lead blanket, and then you run across the room to press the button, right? It's very dangerous. Even more dangerous are gamma rays, which is supposedly what gives Superman his powers. But if you actually try that in real life, you will just get completely obliterated. Like, run away from gamma rays if you ever get exposed to them, right? And if it ever hits the planet, well, there's nothing we can do because they are so high energy that they will go miles deep into the crust as well. There's some there's a doomsday theory that says that some mass extinction events were caused by a gamma ray burst from a nearby supernova. We don't know, right? And we never see it coming because it's light. It travels at the speed of light. So, really interesting stuff. And of course, if we live near a black hole, we have the cosmic rays, which at that point, if you're near a black hole to begin with, I mean, you have other things to worry about, right? But all of this encompasses the electromagnetic spectrum, and we interact with it, and we only see a small part of it, but we do use the remaining part of it every single day for multiple purposes, like heating up our foods, to listening to music, to becoming Superman, right? I don't know if any of you are superheroes at night or whatever, but that's for you to know and for me to never find out in the future, right? You always got to keep your superhero identity a secret. Alrighty. So what's the main takeaway from this slide? Is that we're interacting with radiation all the time. We have built-in spectrometers on our face, and there is a relationship. As the energy goes up, the frequency goes up, right? You can imagine it as moving your hand up and down in the form of a wave, right? If you're going to make a wave that goes up and down much faster, in other words, the frequency is increasing, you're going to use a lot more energy, right? And if you're going to make a wave that has a longer wavelength, you can see that you're going to require a lot less energy. So you can see the relationship between frequency and wavelength. The shorter the wavelength, the higher the frequency, the higher the energy. You should remember these relationships. You don't have to necessarily know how to use the equations, but you should remember the relationships that as energy goes up, frequency goes up. But look, as energy goes up, wavelength goes down. So energy and wavelength have an inverse relationship, whereas energy and frequency have a direct relationship. And you should remember this. I believe there is a question on the final that asks you what type of interactions these are. Are they inverse or are they direct? So, any questions so far about the electromagnetic spectrum and its wonders? Alrighty. So, how exactly are we going to use this to determine what happens in the molecules? Well, there's something that we learn about in Chem 111A and 111B called energy states. And I'm going to be honest with you, it's not very well defined because even the concept of energy is not very well defined, right? Energy, the ability to do work, the ability to make a change happen, right? There has to be something that happens as a result of energy being transferred. And so in chemistry and in physics, we talk about something called energy states, and we kind of make them very abstract. We say, for example, that there's like n equals 0 or n equals 1. You guys might remember this from 111A, 111B. We have like n equals 1, and then we have n equals 2, right? Think of this like the first floor and the second floor of a building, right? You're always in the ground state. Whenever you're outside, whenever you're in your room, whenever you're at home, you're always in a ground state. The gravity's pushing down, and then the earth is pushing back up, and you're in an equilibrium ground state where you don't sink into the ground, but you don't float up away to space, right? You're always in that stable ground state. And when it comes to electrons, electrons can also occupy certain energy levels close to the atom, and these are called energy states, electronic states. And if you have a wave, a photon that hits that electron like a soccer ball, just like you can kick a soccer ball into the roof of a building, you can also kick an electron to the next higher energy level. It'll be further away from the nucleus, so that interaction is going to be different than if it were closer. So it has a different energy state. That's what we mean by it. And obviously, you can't just teleport from the first floor to the second floor. You have to take the stairs, or you have to take the elevator. So somehow, to go from n equals 1, the first floor, to n equals 2, the second floor, you have to put energy into it. And that's what happens with electrons. You can take a wavelength, a photon of a certain amount of energy, and hit that electron into the next energy state. We call that exciting the electron. It is now in an excited state. And then it can stay there for a while, and eventually it relaxes and goes back down to the ground state. And just like there's a certain amount of steps that you take to get to the second floor, there's a certain amount of energy that you need to put that electron into n equals 2. And of course, you can do that to n equals 3, n equals 4, n equals infinity. But it's not just electrons. There's also states where the bonds of the molecules are vibrating like a spring. And again, you can go from not vibrating, n equals 1, to vibrating, n equals 2. And then maybe instead of vibrating like an accordion, maybe now it's being bent, or maybe now it's kind of wagging around, right? Those are all states of energy. So you can think of all of that as n equals 0, n equals 1, n equals 2, the first rotational state, the first vibrational state. And usually, again, ultraviolet radiation and anything more stronger will actually work with electrons. It will kick the electrons up and down energy states. But with infrared radiation, there's no electrons being moved around. There's the bonds that are being vibrated, like springs, right? So I think that was also one of your pre-lab quiz questions. What does IR measure? Well, the functional groups, but it also measures the vibrational motion of the molecules, because molecules can move left and right, in and out, up and down. They can rotate on their axis, and they can vibrate within themselves. So it's the vibrational motion that matches infrared light. And so when we shine a photon of energy that has infrared frequency at a molecule, the carbon-oxygen bond starts vibrating, or the carbon-hydrogen bond starts vibrating. And that is the energy states that we are measuring here. So let me see. Yep, this is basically what I just told you right now. We just have certain energy photons, and higher energy will interact with the electrons, but lower energy wavelengths interact with the bonds themselves. And so for infrared light, we are going to vibrate the bonds using infrared frequencies. Okay, but that bond is going from n equals 1, no vibration, to n equals 2, the first vibration, n equals 3, the second vibration, and so forth and so forth. So I'll show you guys what that looks like in a bit, but this is how the photon gets turned into something that we can measure with our instrument, right? We are exciting the vibrational states of energy using that energy from the photon. Just like you can kick a soccer ball into the ceiling. It didn't get there on its own. Something had to kick it up there. Well, the photon begins the vibrations, and then we can measure that motion and then graph it. So any questions so far about how the molecule absorbs the electromagnetic radiation? And this is just the background info. You don't have to 100% have a full grasp of this, but like we are going over the basics so we can make sense of what we see later. And again, at any point, if you do have a question, feel free to type it in the chat. Make sure it's addressed to everybody. All right. And again, just a summary of what kind of electromagnetic wavelengths exist and how we use them. We're just going to focus on IR, the infrared. This tells us about the functional groups present in the compound. So next semester, you'll learn about NMR, and then you already have UV-vis spectroscopy in your eyeballs, right? Your vision is just visible and ultraviolet light. So yes, things that look red have compounds in them that have that amount of energy in their bonds, right? Like beta carotene in carrots. It looks orange because the conjugated system absorbs that amount of light and then reflects it back into your eyeball. So it's really cool, really cool. We actually have working instruments in our bodies that we use to find out information about our environment, right? Really cool stuff. Alrighty. So we are going to take something that we know. This is what they do in physics. They build models, mathematical models. We have a spring. I'm sure you guys have all seen a spring, right? It looks like a spiral, a helix, and you can compress it and you can stretch it, or it can stay by itself in what we call equilibrium, right? So we have a spring, and you've probably seen springs in everyday life. You definitely have them in your vehicles. Your shocks are very large, stiff springs that are designed to absorb tons of energy. Literally, your vehicle weighs about 2,000 to 5,000 pounds. So they absorb energy in the thousands of pounds. And then you have like the springs that are inside your pen. They're so weak, you can just pull them apart and deform them very easily, right? But all of these springs behave the same way. If you take a spring and you hang it up and you pull the spring down, that spring is going to oscillate up and down. And if you plot that oscillation over time, you get the wave, right? The wave. And you can calculate wavelength, you can calculate frequency. And so we're going to imagine, if you see the bottom of the picture here where it says HCl, we're going to imagine a molecule as a spring. That will be the bond. And at the end of each spring is going to be the atom. And some atoms are heavier than others, right? For example, chlorine has a molar mass of 35.75 grams per mole, whereas hydrogen has a molar mass of 1.008 grams per mole. So chlorine is a lot heavier than hydrogen. And there's many molecules that have different types of atoms. And so those bonds are going to have different types of vibrational energies depending on what's attached to them, right? But for simplicity, we're just going to imagine that we have a spring, and at the end of each spring, we're going to have element number 1 and then element number 2. And then depending on how this moves around and vibrates, that is going to give us a frequency that we can measure. And that frequency we can plot on a graph and then interpret and say, oh yeah, that is the carbon double bond oxygen frequency. That is the carbon hydrogen bond frequency. That is the oxygen hydrogen bond frequency. Because all bonds can be thought of as springs. They are always moving around, right? We always see pictures of molecules. We always see the models. They're just standing still. But in the real life, everything is constantly vibrating and moving around. So yes, the hippies were right. It's all about the vibrations. Everything is vibrating. Everything has a natural frequency. That is 100% correct. So go talk to your boomer parents and apologize to them. Tell them, yeah, you were right. It's all about the vibes. It really is about the vibes, right? It really is about the vibes. And now we're using them scientifically to learn about matter and to confirm whether our experiments work or they don't. So we're going to model bonds like springs, and then we're going to do a little bit of math to calculate them. But disclaimer, IR takes almost no mathematics at all. So it's just the background that you need to know a little bit of math behind it. So any questions about the spring modeling system? You might have heard about it in physics. We call it the harmonic oscillator. That's the fancy term to say spring, the harmonic oscillator. And if you take quantum physics, we call it the quantum harmonic oscillator. Sounds fancy, but it's just a spring. That's all it is. All righty. Okay. So here's the instrument. If you go do a TLC plate next week, you can go and take a look at the instrument. It's actually tabletop size. We've gotten down to the size of a small desktop computer. It's really amazing. And so the way that this works is you take your compound. It could be solid, it could be liquid. I don't think it can be gas, but you put it right here in this red circle. And this thing right here, the detector, you simply clamp it down and it makes contact. And it shines infrared radiation from a range of frequencies, and then we measure how much of those photons go through. If they get absorbed, there is a vibration happening. If they don't get absorbed, well, we haven't matched the energy, right? So nothing is happening. Remember, every energetic state requires a specific amount of energy. So the bond will not vibrate unless you have that exact amount of energy, right? You cannot go to floor 1.5. You only go to the first floor or the second floor or the third floor. This is not Harry Potter. We don't have a platform 9 3/4 here, right? Everything is integer values. So we measure that infrared radiation, and then we plot the absorption or the inverse, which is transmittance, how much of it goes through. And we do this on an XY graph. And then, based on what we observe, we see the molecule's fingerprint. Every molecule has a fingerprint in IR. And this fingerprint is what allows us to identify what the molecule is, right? So I'll explain more a little bit, but real quick, I want to show you right here, circling in the red. You see that symbol again, mu bar. And notice the units. The units are centimeters to the -1. In other words, it's 1 over centimeters. Normally, we measure wavelengths in meters. That is the standard SI unit. But here, whoever developed this method decided it would be good to do it in inverse centimeters. So normally we have a regular mu, that's called frequency, but mu bar is specific to IR, and that has a name. We call that wave number. Wave number. So if you look down here on this graph on the x-axis, you see that it says wave number. This is your mu bar. And you look at the units, centimeters to the -1, right? The reason we use mu bar rather than just lambda, rather than the wavelength, is because remember that energy and wavelength are inversely related, and that can get confusing. So it's better to just have a direct relationship. Energy and wave number are directly related. If energy goes up, the wave number also goes up. If energy gets doubled, the wave number gets doubled because the wave number is just a frequency, right? So they have the same relationship, frequency. And this makes things easy because if you look at this graph, I'm going to use the color purple. It starts at 400 wave numbers and it goes to 4,000 wave numbers. And if the number is big, the energy is big, right? Big number, big energy. Small number, small energy. And this is very useful because now the numbers, actually correspond to what they are. We don't have to think about any opposites or anything, right? So on the x-axis, 4,000 means high energy. And that should be obvious. 4,000 is a big number, so 4,000 is big energy. 400 is a smaller number, so 400 is a smaller energy. All right? So now we can see the range of energies on the x-axis. And energies of what? Energies of what? This whole time I've been telling you we're going to use IR to measure something. What are we measuring the energy of? Any guesses? We have a photon that we shine at a molecule and it does something to the molecule. Oh, we have an answer in the chat. Vibration. Yes, thank you, Zina. Yes, thank you, Ruben. Yes. The vibration of the bonds. The vibration of the bonds. So for example, we might have a carbon double bond oxygen. We might have a carbon carbon. We might have a carbon hydrogen or an oxygen hydrogen. These bonds vibrate at a specific wave number. And when they vibrate, you can see that they produce a signal. These peaks, we call them. These peaks right here are specific vibrations of specific molecules, of specific bonds, I should say, right? So the x-axis is the wave number of the vibration. In other words, how strong is that bond? How strong is your bond? If you have a strong bond, you need more energy to vibrate it. So your wave number is going to be higher. Does that make sense? The x-axis measures bond strength. We should write that down somewhere. I'm gonna use orange. Yeah. X-axis equals bond strength. So depending where you see the peak, that tells you how strong that bond is, right? The x-axis tells you the strength of the bond. Bigger energy, bigger wave number, smaller energy, smaller wave number. Very straightforward. All right. So what about the y-axis? What does the y-axis tell us? Well, before I tell you what that means, we have to talk a little bit about that magical concept that I told you guys about the first semester. It starts with a P, and it's called polarity. Because not only can bonds behave like spring, but bonds have either polar bonds or non-polar bonds, right? We learned this in 111A. Bonds can be polar or non-polar. And so when you're vibrating that bond, you're changing the dipole moment of that bond. All right, so how does that affect the y-axis? Let me go ahead and clear these drawings. All righty, so In order to be visible in the IR spectrum that we take with the instrument, the bond has to have a dipole change. There has to be a change in the dipole. So some molecules you might remember from 111A, like H2 or N2 or Cl2, these are diatomics. And so if these molecules vibrate, well, you have a hydrogen and a hydrogen, same mass, same electronegativity. When they vibrate, there is no change in dipole. So these are not visible. These do not show up in the spectrum that we look at because there's no change in the dipole moment. And if the molecule is symmetrical and it vibrates symmetrically, they will also not show up on the IR spectrum, right? I'll explain more in a bit regarding that. But the main point is there has to be a change in the dipole moment. So if you remember from 111A and 111B, some bonds are capable of forming hydrogen bonds like OH or NH or FH. And, if you want to be a quantum chemist about it, yes, even CH can technically hydrogen bond very, very, like, it's a very small extent, right? CH is polar, but we don't really consider it very polar, but it does have a dipole change, so we do observe it. And so you see, oxygen is more electronegative than nitrogen. Nitrogen is more electronegative than carbon. So if you were to plot these bonds, you're going to see that OH has a wave number that is bigger than NH, and this is going to be bigger also than CH, right? I think I misspelled that one right there. There you go. But also on the y-axis, you're going to see that this peak is going to be much bigger than this one right here. And that's a general rule. Not always, right? There's always that one or two side interaction that the molecule has depending on where it's from or what it's doing. But in general, the bigger the change in the polarity, the bigger the y-axis. We call that intensity, right? Intensity. Let me write that down. Intensity. And this is going to be your y-axis. Intensity of what? Intensity of the change in the dipole. The OH is a very polar bond. If it vibrates, it's going to have a big change in the dipole. So it's going to have an intense y-axis signal. And NH is a little bit less electronegative, so when it vibrates, it's not going to have as much of a change in the y-axis. And CH, well, CH is one of those, there's so many of them that the effect kind of cumulatively adds up, right? Every organic molecule has CH. That's the rule. Carbon likes to make 4 bonds, and whenever there's no more bonds available, it'll bond to itself or to hydrogen. So there's so many CHs that we just see a large intensity even though there's not a big change in the dipole moment. So the intensity is the y-axis and the bond strength is the x-axis. So if I go back real quick, and then I think I can clear the drawings. Yeah. So now you see the wave number on the x-axis, and you see the y-axis, some peaks are larger than others. And so, for example, I'll give you a sneak preview into what we're going to be learning. This one right here, this peak, this is an OH vibration right here. This is an OH peak, this whole thing. And these peaks right here, these are your carbon-hydrogen vibrations. And these ones here are probably some carbon double bond carbon vibrations. That is what we're going to be learning pretty soon. We make this plot so we can measure these signals, and each one of these signals tells me what types of bonds are present in the molecule, and their polarity and their strength. And yes, polar bonds are generally some of the stronger bonds in general. So polar bonds are also strong bonds. Even though they're single bonds, they are strong bonds. So any questions about this so far? This is like the fundamentals right here. Alrighty. So again, just to summarize, x-axis, bond strength. Y-axis, intensity of the change in polarity. That's what we are measuring. All right. So this is a picture that's supposed to show you how the molecules vibrate. So I'm actually going to show you some really cool animations instead of just showing you the slide right here. So I'm going to stop sharing real quick, and I'm going to share this website that I want you guys to use. So here we go. This website is called CHEM223A, and it has different organic, examples. So you can use this when you're learning your lectures, nucleophilic substitution, electrophilic addition, aromatic heterocycles. Next semester, you're going to do Diels-Alder reaction. You can use this website. I still use this website. If you click where it says structure and bonding, and you scroll down to where it says molecular vibrations, you will see there's these example molecules, and you can see their vibrations and see their wave numbers. So I'm going to get started with water. Here we go. You see this water molecule, sp3 hybridized, 2 lone pairs, angle of 109.5 degrees. 104 point something actually, but it's 109.5. So, how does this molecule vibrate? The bonds are like springs, so the bonds are gonna compress or stretch, and they can do it together or they can do it one at a time. And they can also bend and they can also wag around. But we're gonna show you the main ones only. So, you can click here where it says show vibration frequency. And you see we have 3 options. And you see the units are in centimeters to the -1. Those are wave numbers. That is the frequency in wave numbers. And you can use the equation to turn it into energy. Yeah, you can do that. So let's check out the first one. There we go. So this is called the bend. If you see down here at the very bottom, this is called the symmetric bend, mu number 2. And there it is. So you could think of your head as the oxygen molecules, and you can stretch out your hands, right? Like your hydrogen molecules, and your arms are going to be the bonds. And you can kind of like bend them together. You can kind of like bring them together like this, right? Symmetrically. So this is creating a vibration, and that vibration has a certain amount of energy. And when we plot it on the graph, we will see a peak at this wave number, and it might be intense or it might be weak depending, right? This is a bending motion. So bends generally have lower wave numbers than stretches. Bends have lower wave numbers than stretches. But this is one example of a bending motion that water creates. And this happens at 1711 wave numbers. So you can see how it moves, right? And this is real, by the way. We've measured this. We've modeled this. And if you look at the next one, there's a big jump. It goes from 1711 wave numbers to 3730. So let's click on that one. All right. So you can see now it's not bending towards itself. Now it's actually stretching, right? It's compressing and relaxing. This is called the symmetric stretch. And this happens at 3730 wave numbers. So again, it's almost like your arms are like coming in and out. And these are the hydrogen molecules and the hydrogen atoms, and your arms are the bonds, right? So that has a frequency. We can measure that frequency and we can plot it. And if we see it, we say, oh yeah, that is the OH stretch. This is water's OH symmetric stretch. And it happens at 3730 wave numbers, you see, symmetrically. And then we have one more, and you can see this one is also a stretch, but this happens asymmetrically. One of them is out while the other is in. You see that? So this is also going to have its own frequency, its own wave number, and this is going to have its own signal as well, right? So here's a fun business idea for you guys. Open up a yoga Pilates studio and offer people the chance to stretch like the molecules, vibe like nature does, right? Do the symmetric water stretch, the asymmetric water stretch. Yeah, stretch like the molecules do. It's all about the vibrations. And so, yeah, molecular yoga. Really cool stuff. And this is with a simple molecule like water. Let's see what happens with something a little more complicated, like ammonia, NH3. See? NH3. So it's also sp3, based on tetrahedral, 1 lone pair. Let's check out the frequency. You can see we have a lot more options. Just adding one more atom has increased the number of vibrations. So we're going to see more signals for ammonia compared to water. We're going to see at least 1, 2, and 3, 4, 5, and 6 signals here. So let's take a look at the first one. Look at this one. So very similar to the water bending, right? Except this one is bending downwards. It's a trigonal pyramid, so it's bending downwards symmetrically. And this happens at 1132 wave numbers. And this is a bending, there's no stretching, so it happens at a lower wave number. And you can see how it looks, right? There's another one at 1727, and you can see this one is like when you're doing like those crunches with the machines, right? One of them is going away and the other one is coming down. So again, molecular yoga definitely can do it. Here's another one. Look, it's kind of like moving side to side, like back and forth, like a dog that is going to the park and is sniffing around, right? This is definitely an asymmetric bend right here. And it shows you how the more atoms and bonds you have, the more types of combined complicated motions you can have. And this is where the fingerprint comes from. Every molecule has its own motion, its own vibrations. So when we take the spectrum, we see the fingerprint IR of the signals. Here's another one. Oh, that looks nice right there. Look at that. Look at that. You just want to wake up and like Mr. Incredible, just have someone stretch your back out like that. Like that would be nice. Yeah, very nice. So this is the symmetric stretch at 3433. There's another one that is asymmetric, right? The arms are coming in and you're stretching out your back. And then there's one more where one of them's not even stretching and it's really just like, only your shoulders are moving and your torso standing still, right? So again, go and play around with this website. Go and check out all the molecules, see how they vibrate, see how they move, get an intuition for it because I don't want you guys to just look at the IR spectra and see a bunch of squiggly lines. That's one of the things that I have with science right now. A lot of science is just showing graphs and figures and people see squiggly lines and they're like, wow, I'm sure that means something. They mean something. They mean something. And sometimes the graph doesn't show what's actually happening there, right? Like you can look at a graph and you have no idea that the molecules are dancing if you don't take the time to appreciate the concept and the theory, right? So again, this website is called CHEM223A. You can just type it in on Google, CHEM223A. Go on structure and bonding, molecular vibrations. There's all sorts of molecules that you can play around with. And I'll finish off with this one here, just so I can show you. Benzene, C6H6, right? Single double bond alternating, very symmetrical. So how many vibrations do we have? Let's check them out. Look at that. We have a lot more signals, a lot more vibrations because we have a lot more atoms. So I'm just going to show you some main ones. Let's look at the highest energy one right here. Look at this one. Again, that looks real nice right there. Just like a nice symmetric stretching of all the bonds. That looks good. That looks real nice. And this is the highest energy vibration, happens at 3385. Let's take a look at this one. This one is kind of asymmetric. All right. Let's see this one at 1762. This one's more like a wagging, like wiggling kind of motion, right? It's more like just moving around. And then let's see at the lowest energy one. Yeah, so this is called out of plane bending. All of the bonds are bending out of the plane of the molecule. You see that? And this one is happening more asymmetrically. Yeah, see now it's just starting to wiggle around in interesting ways. Yeah, so again, the more complex the molecule, the more unique vibrations and the more signals it'll show. And again, that gives us a fingerprint. So this is what we are putting on that graph. Those squiggly lines that I'm showing you, this is what they represent. They represent the intensity of the vibration in the dipole, and they represent the strength, right? Is it a single bond that is vibrating? Is it a double bond that is vibrating? Is it a triple bond that is vibrating? What kind of vibration is it? Symmetric? Is it asymmetric? Is it a bending vibration? Right? Does this make sense to you guys? Do you understand kind of what we are measuring here? I don't even know how this one is moving. Yeah, different types of motions for sure. And then there's the bending motions. Yeah. So play around with the website. I'm sure you guys will have fun, but I'm gonna go back to the slides now. Let me see. Yes, thank you guys. Alrighty, I'm glad this is making sense. So back to the slides. Continuing on. Okay, so hopefully this picture has a little bit more life to it now. Rather than just seeing them and seeing the arrows and being like, okay, now you kind of know what it means. You see the symmetric stretching, the asymmetric stretching, the in-plane bending vibration, the out-of-plane twisting, wagging. There's many different names for it. And again, only the ones that have a change in the dipole are going to produce signals. So in the example of carbon dioxide, if you have a symmetric stretch where the dipoles cancel out, you're not going to see a signal. There is no net change in the dipole. But if it is an asymmetric stretch, well, one of them is currently positive while the other one is near zero, and the other one is negative, and the other one is near zero. So you are going to have a change in the dipole. The asymmetric stretch in carbon dioxide will be visible. So it all depends on that change in the dipole as well. All right, the y-axis. All righty. So before we go in, just one more overview. Again, we don't expect you to actually know this equation. We don't expect you to actually plug in numbers. But for those of you who are more formula mathematically oriented, this is Hooke's law in physics. And again, each vibrational state is just a level of energy, right? You saw all those different types of vibrations. Some require more energy than others. There is nothing in between. It has to match that energy. So we have the force constant in this equation. That is the bond strength. Single bonds, double bonds, triple bonds, right? Triple bonds are generally stronger than double bonds. Double bonds are stronger than single bonds. So that number will be bigger. And then, of course, we have the reduced mass. In other words, where is the center of that spring? If both of them have the same atom, it's right at the center. If one atom is bigger than the other, it's going to be closer to the heavier atom, right? That's just center of mass. If you've ever tried to balance something, you know that there's something called center of mass. And so all of these things get taken into account. And yes, we can predict where it'll vibrate and we can predict what kind of vibrations it'll have. But you can take thermodynamics and you can take statistical chemistry if you guys are interested in that stuff. But again, we just want to show you that all of this is real. There is a real physics and reality foundation to all of this. This isn't stuff that we're just making up. So when we're looking at these graphs, they mean something. They mean something real, and they give us real information. Okay? Alrighty. So that was the theoretical background. Now we're gonna learn to actually read the IR. So this is what you'll be doing on the quiz in the next 2 weeks. And this is what you're gonna see on the final exam and next semester. You're gonna be constantly given these spectrum. The plural of spectrum is spectra in Latin. Spectrum, spectra. So spectra is plural. You're going to be given many spectra, and you're going to tell me what is here. Is there an OH bond? Is there a CH bond? Is there a double bond? What type of functional group is it? Is it a carboxylic acid? Is it a ketone? Is it an ester? You will know how to tell me that information by looking at these squiggly lines. They mean something. So, I promised you guys there was going to be no math. And it is true. We only look at 3 things for now. We look at the wave number, the x-axis. That gives me the bond strength. So I'm going to write this down as I'm telling it to you guys. Hold on. Got to do my annotations. So here we go. Wave number, bond strength. Intensity. This is your y-axis. This tells you change in dipole. Go change in dipole. The last thing is we have to talk about the shape of the signal. And this is where the human element comes back in. We all know adjectives. So we're going to use our adjectives to describe the signal. So we're going to be using words like strong or weak. We're going to be using descriptor words like broad or narrow or sharp or needle. We're going to be using like high energy, low energy, medium, those types of words. So for example, here's how we talk about signals in organic chemistry. You'll see I'm going to start with this signal between 32, right here, between 32 and 35, roughly. This is kind of a broad signal. And you see that it's a big signal. So you see the y-axis, if you look at the number, there's only about 15 to 13% transmittance. Well, that means that there's a high absorption. That's why you see a big signal. So just look at the size of the signal, right? If you see a big signal, that's a strong signal. So this is going to be described as strong and also broad. A strong, broad signal between 3200 and 3500 wave numbers. That is how we talk. That is how we discuss this graph, right? So here are some very strong, sharp signals, right? Very strong, sharp signals at around 3000. This is how we talk. I'm just giving you sentence examples. Here is a potentially medium, strong, sharp signal at 1500. And most likely this is a carbon-carbon double bond. I'll tell you later how we know. So this is how we describe the graph. This is what we look at. This is what we see. Okay, we look for the size, the intensity, the shape of the signals, and we look where they are located, and then we talk about them. And then we can say this strong broad signal is an OH bond. This very sharp signals are CH bonds. This medium sharp signal at 1500 is a carbon-carbon double bond. That is how we're going to be talking about these graphs. So any questions about the language, about the adjectives, anything like that? Alrighty. So you should memorize this. A lot of people nowadays in school tell you, you don't need to memorize this. You don't need to memorize this. Why not? Why not memorize it? Once you know it, you know it. You will always remember it. You never have to worry about consulting a book. You don't have to say, I don't remember. You don't have to worry about, oh, the stuff they gave me on the final didn't have enough information. Study it now. Memorize it now. And especially if you're going to stay in science, this isn't going away, right? You know your ABCs. You learned it once a long time ago and you never forgot. And now you know how to read. And if you were to try to guess how to pronounce something in like Spanish or another language, you could even try to do so with some accuracy. So some things are worth committing to memory. And if you're going to memorize anything, I would say memorize this general table. Memorize the regions, right? You don't have to memorize everything blindly. You can reason your way through it. So for example, we'll see, I'm going to start using red. Between 600 and 1400, we call this the fingerprint region. Now, I was taught that anything less than 1000 was the fingerprint region, but this book and many of your professors say 1400 and below. So stick to what your professor says. But there are some useful signals we're going to see between 1000 and 1400 that we can use to identify stuff. That's why I don't really like dismissing them as fingerprint region. But in general, it's in the lower wave numbers, right? And remember, low number, low energy. So these are going to be the weaker bonds, right? The carbon-carbon single bond, the carbon-oxygen single bond, the carbon-nitrogen single bond, right? Just single bonds in general. And remember, these are most likely going to be bending motions rather than stretching motions. So usually the single bond stretches, the single bond bends are going to be less than 1400. And remember, double bonds are stronger than single bonds. So you're going to find those between 1600 and 1800. Here you're going to find your alkenes, your carbon-carbon double bonds, your carbonyls, which is your carbon oxygens, your nitriles, or I don't know, I think there's a different number for carbon nitrogen double bond. I actually don't remember it. Your nitrile would be your carbon nitrogen triple bond, which would be between 2000 and 2500, right? So again, it's a good idea to know these things. It's a good idea to know where they are. You don't always have to commit it to memory 100%. You can just know, well, the triple bond is stronger, so it's going to have a bigger number than the double bond. And the double bond is stronger, so it's going to have a bigger number than the single bond. And the polar bonds are the strongest. Even though they're single bonds, they're the strongest of them all. And they can hydrogen bond. So that's more energy you have to put in to vibrate the bonds. That's why we find these at the very, very end, closer to 4000, 3000 in the upper bounds, right? And there's only so many different types of bonds you can make as an organic chemist, right? We only have these possible bonds that can exist in a molecule. So yeah, it'll take a bit of looking at it and referencing it, but the sooner you kind of get an intuitive understanding or memorize it or keep it in your brain somewhere, the much better and much easier it'll be. This is actually a quick process. We don't spend a lot of time as organic chemists looking at an IR. We take an IR in about 4 minutes, we print it out, we look at it for about maybe 5 more minutes, and then we move on to the next part of the experiment. It's crucial. It helps us know if we're heading down the right path when we're making a molecule, but the analysis itself, once you know it, is pretty easy and straightforward. So I know we're just learning it. It's our first time probably ever thinking about the molecules are vibrating. So I don't expect you to understand this just from today. But this is the first day of the rest of your IR studies, as long as you're going to be a chemist or a biochemist, or you're going to be a forensics analyst or something like that, right? Thinking about this is helpful, even just as training. Alrighty. So any questions about this? Okay. So let's get started then. If you don't know your functional groups by now, start learning. This is a good time to start learning. They are not going away. So we have alkanes, alkenes, and alkynes. This is just your simplest molecule. This is your carbon hydrogen molecule, right? So you could have like, hydrogen, carbon, hydrogen, hydrogen, carbon, carbon. It could be as simple as 3, 2. It could be methane by itself. It could go on to infinity. You can have an infinite carbon chain. Plastics are made out of very long carbon chains. That's why they bend. That's why they're flexible. When you bend the plastic, you're bending the chains of the molecule. So these are just hydrocarbons. And what kind of bonds do they have? They have hydrogen-carbon bonds, right? It's the hydrogen-carbon bond. That's the bond that's going to vibrate. So that's the bond whose signal we look for. So you can see in this spectra right here, we have this peak, these sets of peaks right here at around 3000. These are your carbon-hydrogen stretches. Carbon-hydrogen stretches. Every organic molecule has this because every organic molecule has carbon by definition. So you are always going to see these peaks in every IR spectra of every organic molecule that you're going to take. These will always be there. So you have to know when to pay attention and when to ignore them, because these are always going to be there, because every molecule has hydrogen-carbon bonds. So if we don't see any other signals, and this is all that we see, we can deduce that it is just a simple hydrocarbon, like an alkane, an alkene, or an alkyne. Notice how the spectra looks pretty simple. There's not really many peaks. There's not really many things happening there, right? It's just maybe 2 or 3 peaks and that's it. So this tells me there's only really a carbon-hydrogen bond happening somewhere around there. And remember, triple bonds are stronger. So if you look down here where it says alkyne at the bottom right, you'll see this peak, this CH. This is a CH peak right there. And if you have a triple bond, your hybridization is sp. So this is an sp-CH stretch. And it's a triple bond, so the wave number should be stronger. And yes, it has a value of around 3300. And it's a medium sharp peak. You can kind of see it right here. There's actually not even medium. I would call that weak. That's a weak sharp peak. And it's more to the left of the CH stretches at 3000 because the triple bond is stronger. You should see the wave number be bigger. And then if you look at the middle, you see the alkene. This is your sp2 CH stretch. And this happens at a smaller wave number, 3100, because double bonds are weaker. So their number should be less than triple bonds. And finally, at the very left, you see just a regular old CH single bond. It just blends in with the signals. This is the one that we see. These are always present somewhere at around 3000. And so you can see the trend. The number goes up as the bond strength goes up. For you hybridization fans, as your S character goes up, the higher your wave number. So sp only has one p orbital, sp2 uses two p orbitals, right? So you can see that as the number of p orbitals goes up, the wave number goes down. But if this is a bit confusing for you, then that's all right. We're just offering multiple perspectives. In short, you should just know your triple bond is stronger than your double bond. Your double bond is stronger than your single bond. So those numbers are going to correspond as well. But the CH stretch is always somewhere around 3000, and you should know how to identify it and when to ignore it. And this is what it looks like. So here's a few examples. This is your gasoline right here, octane. Octane, high octane gas, right? A lot of carbons, a lot of bonds to break, a lot of energy being stored. It's just CH. There's nothing else. This is just CH. So the only thing you should ever expect to see for octane are CC stretches and CH stretches. And I can keep going, but you should know how to find the hydrogens. And that's all you see. So look, here at 3000, we have, at around 3000, we have our CH stretches. All of these, all of the peaks, right? They kind of blend together into one signal, but they're different sets of peaks. So we just call it a set of peaks. If you've ever been to a cave, I actually call them stalactites because they come down from the ceiling like those cave peaks. So I call these the stalactites. That's not the official name, but that's one way I refer to them. These are always CH stretches. These are always there. Here at around 1400, 1200, we have some bending, some CH bending. I'm going to be honest with you, we don't usually know, unless the molecule is simple, which ones they are specifically. We don't actually need all the signals. We just need to look for the important ones. So at some point, there's going to be more signals, and you might be tempted or you might get overwhelmed. You'll be like, oh, how do I know this is a CH bending? Sometimes you don't. And if you don't know, you don't say that you do. You just say, I don't know. We don't pay attention to those peaks, right? So don't try to assign peaks. Don't be ChatGPT and confidently give an answer. Just say, I don't know. And sometimes you might not know because it's not an important peak. There's other peaks we can look at that will give us the information we're looking for. But for octane, we would just look for CH stretch, nothing else. And that's all we see. Let's take a look at the next example. This is a hydrocarbon that we call aromatic. And again, you're probably starting to talk about this in your lectures for now. When we say aromatic ring, we mean benzene. This. It is a hexagon usually, and it has alternating single and double bonds. So this is what we mean when we say aromatic ring for now. Only in the context of IR. Okay, later on, you're going to learn how to determine aromaticity in compounds. The first thing I want you guys to notice is you see the spectra looks a lot sharper. So the spectra is sharper overall. The peaks look more needle. Compare this to the previous one. Look at octane. They're still sharp, but like there's kind of more of like a wideness to them. You see, they're more wide. Like the intensity is more intense. Look at these. The intensity is less, and the peaks overall look more spiky, more needle shape. There's a lot more roughness to it. So this, if you see a very sharp, very rough spectrum, you might suspect you have an aromatic ring somewhere. And usually you'll see the intensity of the stalactites, the CH stretches at 3000. There's going to be less intensity. Sometimes, not always. There's also going to be these bands. I call them foothills, but they call them combination bands. So right here. Not always. Not always. But if you see some sort of pattern like this, usually you have an aromatic ring. And of course, the signal you can use to confirm for sure will be your carbon-carbon double bond signal. So this peak, I'm going to use blue. This peak right here. This is your carbon-carbon double bond stretch. That's your vibrating, your vibrating molecule, the vibration of the molecule. That is the carbon-carbon double bond. So that's a very sharp peak, medium intensity. Usually you find this at 1500. Plus minus some here and there. And so if you see all of these things happening in your spectra, you probably have an aromatic ring in there somewhere. So this is toluene, CH3. If you put nitric acid on that 3 times, you get trinitrotoluene, TNT, explosives. So this is the starting material. Yeah. This is how you would confirm that it actually is toluene before you start making things randomly here and there using IR. So any questions about the difference between aromatic hydrocarbons and we call it aliphatic or just straight chain hydrocarbons? Any questions about the spectra, the signals? One of the most common questions I get is, how am I gonna ever learn all this? How am I gonna memorize all this? Again, you kind of memorize, but you also just do many examples. The more examples you do, the more you interact with these signals, the more familiar you become with what they look like. So this is one of those cases where repetition really is a good way to study and learn this. You just do many, many, many examples. All right. So next one. This is a big one, guys. This is like I want you guys to like if you learn nothing else today, if you forget everything about IR, at least remember this because you guys remember that meme from biology, right? The mitochondria is the powerhouse of the cell. You guys remember that like nothing. For organic chemistry, remember this, right? Remember the carbonyl. Remember what the carbonyl is. So, the carbonyl, when I use this word from now on, this is a new word we're learning. We're learning how to speak organic chemistry. When I use this word, the carbonyl, it is a very specific word. It's so specific. It means only this and nothing more. This means carbon, double bond, oxygen. That's it. If you hear the word carbonyl, you are talking about a carbon, double bond oxygen. Nothing more. This is it. The word carbonyl, this is the definition. Carbon, double bond oxygen. That is its name. That is its name. So when I say the word carbonyl, I'm talking about this guy right here. When I say the word carboxylic, that's something different. When I say carbon, that's the element. This specific word specifically means this right here. I cannot emphasize that enough. Why? Why am I making such a big deal about this? Because there's many functional groups that are made up of a carbonyl and something else. So if you're going to talk about the functional groups, you have to address it by the right name, right? Every one of us has a name. These bonds have names, and you have to use the right name. And yes, it can be confusing, right? But you have to use the right name because the name tells us the structure. So it has to be the correct name, all right? That's why. So when I say the word carbonyl, I'm talking about the carbon, double bond, oxygen. There are functional groups that contain a carbonyl. And they create a family of carbonyl functional groups. And you can see the names down at the bottom of the slide. So I'm going to go ahead and show you now. Here they are. Yes, you need to know the names. You need to know, if I tell you aldehyde, you need to know this is what it looks like. You need to know, if I say carboxylic acid, this is what it looks like. You need to know these structures at some point. If you're taking organic chemistry, you have to know these by memory, by heart. You have to know how to draw them. All right, this is a good time to learn them. The carbonyls make up a family of functional groups. This is the family. They are the aldehyde, the ketone, the ester, the carboxylic acid, and the amide. And the carbonyl is a polar bond. So the carbon double bond oxygen is going to vibrate at around 1700 plus minus 50. That's my rule. This is what I teach. This is what I've used. Of course, there's always those exceptions, you know, a little bit more, a little bit less. In general, this is a good rule. The CO stretch happens at 1700 plus minus 50. So when you point to that signal, you have to tell me this is a carbonyl signal. This is a carbonyl peak. And then the next question is, what type of carbonyl? What type of carbonyl is it? So just like we have first names and last names, right? So I know that one of the most common Hispanic last names is Garcia, right? So if you go out to the market and you say, "Hey, Garcia," everyone's going to turn around, right? So you have to call it by its first name as well. You can't just say Garcia. You have to be like who? Like David Garcia, Jose Garcia, Eduardo Garcia, right? These compounds have names. Call them by their names, right? Let's be polite. Call them by their names. And so you can have an aldehyde carbonyl. You can have a ketone carbonyl. You can have an ester carbonyl. You can have a carboxylic acid carbonyl, an amide carbonyl, right? The carbonyl is the last name. So, hi, my name is aldehyde carbonyl. Hi, my name is ketone carbonyl. My name is ester carbonyl. My name is carboxylic acid carbonyl. These things have names. Call them by the right name, right? The carbonyl is the last name, and the functional group is the first name. So when you tell me this is a carbonyl signal, I'm going to ask you which one, and you're going to tell me it's a carboxylic acid carbonyl. Okay? Any questions about this? This is just language. This is just like learning how to talk about these things. Now, I know the slide shows you numbers, but this is just kind of to show you how the signal can vary. This is why I give you the rule. 1700 plus minus 50. Stick to that, and you'll be good 95% of the time. So, yes, we're going to look for a carbonyl signal, and then you're going to tell me what type of carbonyl it is. That's going to be another signal. All right? But first, we're just learning about carbonyls for now. Any questions about the carbonyl before I move on to the examples? The carbonyl is a big deal. If you eliminate the possibility that you have a carbonyl, you have eliminated about 50% of the functional groups, and you're much closer to a correct answer. So this peak is very important. It points you in the right direction. Alrighty. So let's take a look at some examples. Here we go. We have two molecules. We have 2-heptanone and butyraldehyde. And just like you can see in the name, 2-heptanone is a ketone. That's why it has the "one." So this part of the name tells me that this is just a regular ketone. And then here, butyraldehyde, well, it's also in the name. It says aldehyde. So this tells me that there is an aldehyde in here. That is an aldehyde right there. So based on the name, I know what kind of carbonyl that I am expecting. So take a look at this top one. It says 2-heptanone. You see it says 1718. And look at the signal. Take a minute and like look at it. How would you describe this? What adjectives would you use for this signal at 1718? You can type it in the chat. You can say it. Like, what are some words you would use for the signal here? All right, we got someone in the chat. Very strong and sharp. Yes, yes, definitely. Thank you, Riley. Yes, very strong and sharp. I would say yes. So that is your carbonyl peak. Very iconic, very characteristic. Like once you see it, once you learn it, you can't really miss it, right? This is like not knowing the Beatles. This is like not knowing Buddha. This is like not knowing Jesus. This is like not knowing, I don't know, like I don't know who else, right? Some things are iconic. This is the iconic signal of the IR spectra, the carbonyl peak. If you find it, you have some carbonyl functional group. If you don't have it, you don't have any of them. You can't because the signal is not there. And now you can guess other functional groups. So it's very important that we know what the signal looks like, where to find it. I say go to 1700 and start looking around. If you see something very sharp, very strong, you have a carbonyl. And then the next question becomes what kind of carbonyl? Well, let's take a look at the bottom. You see once again, at 1720, very strong signal. Maybe not as sharp, but I would still say, strong for sure. Strong, Sharpish, not really sharp, but sharpish signal, but definitely strong. It's almost touching the x-axis. So it's a carbonyl, but how do we know if it's a ketone or an aldehyde? Well, the aldehyde also has this other signal here. I'm going to use the color green. This carbon hydrogen of the sp2 carbon containing the carbonyl. See, the language is starting to get technical. This CH bond containing the carbonyl, this sp2 carbon, that CH has its own fingerprint. You see, it has two signals, one here and one here, and they happen a little bit less than 3,000. And that is called the aldehyde stretch, the aldehyde CH stretch. And you only look for it if you first confirm that you already have a carbonyl. So if you don't have a carbonyl, why would you look for an aldehyde? It doesn't make any sense, right? You wouldn't go to the gas station if you have an electric car, right? Maybe out of habit. But if you don't have a carbonyl, you don't look for the rest of the signals. You only look for the rest of the signals when you confirm you have a carbonyl. So that's what makes it easier. You don't just go in blindly and start guessing. You say, oh, I have a carbonyl. My next question, which one? I don't see any signals, then it's just ketone. If I see more signals, it's another type of carbonyl. Okay? So any questions about the carbonyl signals so far? There's going to be more. The carbonyl is a big topic. All right. So let's take a look at some more examples. Conjugation. This is another word you're going to be learning about. Conjugation. This word means single bond, double bond, single bond, double bond, single bond, double bond. That's what that means. So when you see the word conjugated, conjugation, that means the molecule has a single bond with a double bond, with a single bond, with a double bond, with a single bond, with a double bond, with a single bond, to infinity, or as long as it needs to be, right? Whenever you see alternating single double bonds, that's called a conjugated system. Conjugated system. That is the language that we use, right? When I went to my first conference, every chemist was talking about conjugation, and we had a Q&A, and I was like, what's conjugation? And they just told me single bond, double bond, single bond, double bond, single bond, double bond. That was the answer. And that's it. So sometimes your molecules are going to be single bond, double bond, single bond, double bond, like a benzene ring. A benzene ring is conjugated because it has single bond, double bond, single bond, double bond. So if you take this benzene ring and you put a carbonyl and maybe a double bond, and then maybe another double bond, and then maybe another carbonyl, this whole thing is conjugated. And if this whole thing is conjugated, it has a special property. The bonds actually share, the electrons actually share between the single bonds and the double bonds because they're alternating. We have resonance. We call them resonance structures. There's many ways you can draw them. And if you average them out, it's like you're spreading butter on a piece of toast. You're spreading out the electrons. So instead of having a double bond, you're going to have a 1.5 bond because you have a double bond and a single bond alternating in the whole molecule. We can average it out into a 1.5 bond. We say the pi bonds are delocalized, right? So instead of having just a double bond or just a single bond, 2 plus 1 equals 3, divide that by 2, and we get 1.5. We have a 1.5 bond. In other words, the bonds get weaker. The bonds get weaker if they are conjugated. Because now, instead of having a double bond, you have a 1.5 bond. It's weaker than a double bond. So the bonds get weaker. And therefore, the wave number goes down. The bonds get weaker and your wave number goes down. Because now the bond is weaker, you need less energy, right? So you see here, you have a regular ketone sitting at 1720, but if you put a double bond next to that single bond, next to that double bond, see? So you have, single bond, double bond, single bond, double bond, single bond, right? This is a conjugated molecule. that signal goes down to 1680. And this is why I think you guys should remember the rule 1700 plus minus 50, because it's not always going to be exactly the same place. It's a guideline, it's a generalized region, right? Don't memorize numbers. Look for the regions, look for the shapes, look for the characteristic peaks. That's the point. Because sometimes there's little things like this, like resonance effects or pi stacking or all that other nonsense, and it changes things. So you got to know how to look for the characteristics, right? You know the difference between a car and a truck. You know the difference, right? So it's kind of like that. Yes, they're both vehicles, but there's some subtle things that tell you the purpose for one or the purpose for the other. Well, conjugation will tell you the wave number is going to go down. So any questions about conjugation? And this happens with carbonyls. That's why it's coming up right now. The carbonyl can be conjugated and its wave number will go down. All right. So let's move on finally to the next functional group, the alcohol. The hydroxide is the proper name, the hydroxide. This one is also iconic, much easier to identify. So this is the actual name. It's hydroxide, like sodium hydroxide, just OH, right? But when you connect it to a carbon, it becomes either an alcohol or a phenol, right? If it's just an inorganic OH, it can be called hydroxide. But if you say hydroxide, you're not wrong. You're not wrong. We will always know you mean the OH. Alcohols happen in chains, whereas phenols happen in aromatic rings. Okay, so you might see a benzene ring with an OH, like this. This is a phenol. You might see just a 2-carbon alcohol, like this, like ethanol, the one that we drink. This is the alcohol. So when you say phenol, you're telling me there's a ring. When you say alcohol, you're telling me it's just a chain. And yeah, people use them interchangeably, but again, we need to learn to speak properly. There is a specific definition to these things. So if you don't know and you want to be safe, I recommend for now, you just remember hydroxide. Hydroxide is definitely the safe name that you can use for describing an OH. And with practice, you'll know the difference. Yeah, but you also need to know we call them alcohols and phenols. Either way, it's all OH. This is all OH. And so OH is polar, right? Very polar. Oxygen is very electronegative. And it's also strong. So it's going to have high intensity. And it's going to have a high wave number. And sure enough, if you look at our example down here, you can see the OH signal. I'm going to use the color red. This very broad, strong signal, right? Because I would call that strong for sure. Definitely noticeable. You might want to call it medium strong even, sure. But strong, broad, between 32 and 35, this is going to be your OH stretch. Also smooth. I will use the word smooth. You notice many peaks have spikes and edges. This one is just a smooth peak. It's a smooth broad signal. So once you train your eyes to see this and you see it, you know it immediately. You're like, oh, there's an OH. Just like that. So yeah, look for this shape. Look for the shape. Look for it in those regions. And if you see it, you probably have a hydroxide somewhere. And that's what we look for. Everything else we kind of ignore because it's not really important, right? Remember these right here in the green. These are your CH stretches. They're everywhere. In this case, useless. They don't tell us anything. They just tell us that the compound is organic. Well, we knew that. It's organic chemistry. There's this other one here at around 1500. Sorry, at about 1050. There we go. At around 1050, we see this CO. And that CO is just the COH, right? This CO right here has its own vibration, and it happens at around, I'm gonna say 1100. We'll talk more about this one coming up, but I mean, if you have an OH, of course you're gonna have a CO. It's not really that useful. It's nice to see. It's good practice, good training, but for now, for this specific example, it's not really useful. So really, the only thing you gotta look for is this signal here, the one between 32 and 3500. So any questions about the OH signals right here? This is spectroscopy. This is what the field looks like. And you're gonna do this with NMR next semester too. All right. Okay, so next example then. This is where, once again, the language becomes important because now we go back to the carbonyl. If you have a carbonyl plus an alcohol or a hydroxide, right? So a carbonyl plus hydroxide, this gives you carboxylic acid. So if you see the one at the bottom that I drew just now, I'm going to circle it in green. If you see this, this is called carboxylic acid. This is called carbonyl, and this is called hydroxide. They each have their own name, okay? Just like everybody has a first name and a last name. So you have to be very specific, right? Look at the spectra for a carboxylic acid right here. So the first thing you look for is the carbonyl. So here's 1500, 1600, here's 1700. And look at that. We see this strong, in this case, it's a little broad, right? So strong signal at 1700. This is your carbonyl signal. And then take a look over here. We have an extremely broad, very broad, like, I don't know, like the broadest right here. This is almost 1000 wave numbers. That's a very broad signal. And it's kind of smooth and it's a little like spiky at the bottom, right? We call this the wizard's beard. That's the name of this. Not officially, but enough chemists know about this, right? If you've ever seen like Gandalf or Dumbledore, they have like this wizard's beard coming down, right? And it's a little like, sometimes it's well kept, sometimes it's not, kind of triangular. So if you see the wizard's beard between 2500 and 3500, and it's a very broad signal, and it looks like a wizard's beard, and you have the carbonyl, you have a carboxylic acid. This is one of those compounding signals that together tell you what type of carbonyl this is. So then you would tell me, this is a carboxylic acid carbonyl, and this is a carboxylic acid hydroxide. See, it tells you right here, OH from carboxylic acid, carbonyl from carboxylic acid. You have to tell me these things. Sometimes you're going to point to this signal, and you're just going to say carboxylic. Well, I know what your brain was trying to get at, but that's not correct. You have to say carboxylic carbonyl. Because if you say carboxylic, you could be talking about the OH, or you could be talking about the C double bond O. Which one? You have to be specific. These are the rules. I'm sorry, I don't make the rules, right? It sounds very OCD, but everything has a very specific meaning when we're talking about this. So we look for these two signals, and we have a carboxylic acid. Any questions about this one? The rest of the signals we just ignore. Those are not useful. We only look for two signals here. If we see these two signals, we just have a carboxylic acid. Everything else we'll figure out later. All right. So here's another one that we got to learn. This one is called ether. Carbon single bond oxygen. This is called an ether. If there's another carbon like this, you have what's called an ether bridge, but this is just called an ether. It's carbon, oxygen, carbon in the molecule. And so you see that there's this carbon-oxygen single bond right here, carbon-oxygen single bond. This one vibrates at around 1,000 to 1,200. It depends. And it's polar, right? Carbon-oxygen is polar. So this is going to have a high intensity signal. And you can see it's very, very high intensity. Sometimes you're going to see the intensity is very close to the carbonyl. The difference is that this is going to be at a lower wave number because remember, double bonds are stronger than single bonds. So even though this is a polar bond, it is a single bond. It's going to be lower than the carbonyl. So here at the bottom, we have this example. Dibutyl ether. So butyl is 4 carbons. So 1, 2, 3, 4. And then we have an oxygen in the middle. And then another 4 carbons. 1, 2, 3, 4. So that's the compound right there. And this CO bond, that's this one right here in the purple. The CO stretch. And that's what we look for. And that's also why in the OH, in the hydroxide, this peak will show up, but it could still be an ether. Just that peak doesn't confirm it's an alcohol. So it's good to see, but in that case, it's not very useful. Right? Here, we don't have an OH peak, so we know that CO cannot be an alcohol or a phenol. It has to be something else. So that's why it's useful. What are these peaks right here in the red? Somebody tell me. What are those peaks right here? These are present in all molecules. Everything is going to have these signals. What are these signals? It's a stretch, right? What kind of stretch? All right, we got CH. Excelente. Muy bien. Yes, this is a CH stretch. You have to know these. These are everywhere. You're always going to see these signals. So in this case, they don't tell us anything. That's why we don't even bother pointing them out. But you gotta know them. When you see them, you gotta know, yeah, those are there. Cool. I don't need them right now. All right? In this case, you only need the CO single bond stretch. All righty. So next example. What if you have them both? What if you have a carbonyl and an ether? So this is another functional group. Carbonyl plus ether. So we have carbonyl plus ether. This gives me an ester. Ester. An ester is a carbonyl and an ether. And it looks like this. Like that. Obviously, there's hydrogens here. But yeah, this is an ether compound. So we've already used ether compounds in the lab. It was 95% ethyl acetate. Ethyl acetate is an ether. So yes, this would be part of the structure. So ethers are going to have carbonyls at 1700, and they're going to have ethers between 1000 and 1200. If you see those two signals, you know you have an ester. So any questions about this one? Now you can tell me, this is an ester carbonyl. Because you have this CO plus this carbonyl peak. Now you can be specific. First name, last name. Because now you saw the two signals. Usually you pick the strongest signal between 1000 and 1200. You pick the strongest signal and you say, that one is my carbon-oxygen single bond. Because it's polar. It should have the same intensity, roughly the same intensity as your carbonyl. Alrighty. And then if you look down below, we also have methyl benzoate. It has an aromatic ring, so look at the spectra. It's a lot sharper in general, right? Very sharp spectra. You'll notice the CH stretches, the intensity is lower. So that's one of the effects of having that aromatic ring. And also, if you look at between 1400 and 1600s, you have your carbon double bond carbon peaks. Now look at your carbonyl peak at 1700. Right here, 1700 in the red. This is your carbonyl peak, but it's conjugated. Single bond, double bond, single bond, double bond. You see? So the wave number is going to be a little bit less. The intensity might be a little bit reduced. So you don't see very strongly, but you still see very distinctly you have your carbonyl peak. So therefore, carbonyl plus your carbon-oxygen stretches at 1100 plus the spikiness, that tells you aromatic ring, ester, carbonyl of an ester. You have to put everything together. So any questions about this one? So again, I don't expect you guys to just magically know this out of nowhere. Like you're hearing this for the first time. So the important part is you got to practice this. You got to go and look at spectra and work through it and talk your way through it and check against known spectra and always be comparing. We don't just go into this blindly. No chemist can go and look at a spectra and tell you the exact structure of the compound. That is not possible. This is a small piece of a whole puzzle. Okay? So don't think that, oh, I should know the whole formula based off of this. Nope. All you know are the functional groups. Is it a carboxylic acid? Is it an ester? Is it a ketone? Is it an alkene? That is what you can answer with IR. You cannot tell me it's C7H12O5. I don't know if it is. It could be. But that information cannot be derived completely from just an IR spectra. You need more information. Okay? This is strictly for the functional groups. All right. Okay, so this is another functional group that we got to know about. This is called the amine. I know there's a singer, rapper, whose name is Aminé. I think that's how they pronounce it. I don't know. But this is pronounced amine. Amine, okay? And amine is specifically the NH bond. And amine. So if you have NH, you could have NH2. You could have just NH. If you have nitrogen and just carbons, like this is an amide. So amine specifically means nitrogen, hydrogen. And amide starts talking about carbon and nitrogen. That's the difference between the two. So don't call these amides. They're not. And an amide is also a carboxylic functional group. So if you see this, and the R is just a placeholder, it could be anything, right? But this could be NH, this could be NH2, this could just be N and some carbons. This whole thing is called amide because it has the carbonyl. Okay? So if you see the word amine, you're specifically talking about the NH. Any questions about that? Very similar words, one letter difference. That's why. Alrighty. This is one of those compounds that actually gives you some structural information based on the number of peaks. So you could see in this example, hexylamine, you have two NH bonds. So you're going to have two NH signals. Number one, number two, number one, number two. And since you have two signals, you must have two NHs. So therefore you have NH2. And if you look over here at this example, piperidine, right? It's a ring, so it only has one NH. We only see that one signal. This is just one NH right there. So you look for the peak between 3200 and 3500, not strong at all. I would call this weak, actually. This is like a weak signal. Yeah. And also notice it's to the left of the 3000s. These are your CH stretches. These are always there. This is going to be at a higher wave number because NH is more polar than CH. And so that's why you see the number is larger. So if you have two peaks, you have NH2. And if you have one peak, you have NH. If you have no peaks and you think or you know that there's supposed to be a nitrogen in there, then this peak is probably somewhere down at around, I would say maybe the 1200s, maybe a little bit less. The NC stretch. But usually we don't look for those peaks. It's not something you're required to know, but if you don't see these two peaks, then you would look for this next peak, the NC stretch, right? Everything is a process of elimination. So tertiary amines should not have signals here at all. If you see these signals, they can only be NH. They can only be amines. So any questions about amines? How to spot them? Alrighty. And that covers the basics of the functional groups and their signals. So now we go and actually play the game. Now we actually start interpreting spectra. And again, nobody was born knowing how to speak. Nobody was born knowing how to walk. Nobody was born knowing how to ride a bike or drive or write or read. We all had to learn. And so we're just learning how to read something new. We're learning how to read lines and numbers and how to connect them to ideas. Okay, so I just gave you a slight overview of the ideas. Now we actually start looking at the pieces of this and we put it together and we can start saying, oh, that's what this is. That's what this is. So that's what's coming up next. So any questions so far about anything that we've discussed in the lecture? It's kind of a lot of info, but all of that was just to prepare you for this. This is what you actually do, the actual interpretation. Okay. So let me check the time, make sure we're doing good. Yep. Alrighty. So you tell me now. You guys have to tell me now. And ask me and guess, it's okay. What functional groups are present in the spectra based on everything we just went over? And I'm gonna mute my mic, and then somebody gives me an answer on the chat, or you can unmute and tell me what you see. So what functional group is present in this spectra? All right, so Andres says carboxylic acid, and I will say yes, you are correct. Now, why did you say carboxylic acid? What gave it away? The wizard's beard. Exactly. Exactly. Sometimes it's just like that, right? I promise you no math, right? We only look at the numbers so we can see where to look, but we look for the shapes, we look for the general regions, and we say, this is what we see. So yes, you saw the wizard's beard and you said, oh, there must be a carboxylic acid. Well, if you have a carboxylic acid, you must have a carbonyl and you must have an OH signal. So the carbonyl is found at 1700. So I go over here to 1700. Here's 15, 16, 17. And look at that. Here is my carbonyl peak at 1700, just like we learned. And then we see this very long You know, it starts at around 2500 and goes to about 35-ish or so. That's about 1000 wave numbers wide. And Andres said it looks like a wizard's beard, right? I have this I'm not a very good artist, so I'm just gonna draw like the happy face dude. All right. So yeah, that's the wizard and his beard. So if you see the wizard's beard and you see the carbonyl peak, you have a carboxylic acid. And that's it. That's all you can say. Any questions about this? So that would be the answer. Like I would ask you a question on the quiz. I would give you a spectra and I would tell you like what functional groups are here. And then you have to tell me carboxylic acid. And then I might ask you, okay, draw it. And then you just have to draw the carboxylic acid. And that's it. I don't know if this is benzene or C7H, whatever. I don't know if this is, all I know is there's a carboxylic acid here. And that's all we can learn. That's all we can learn, right? So again, I just want to emphasize that this is a partial method to the complete analysis. This is not like a standalone thing. Alrighty. So let's take a look at this next one here. Again, you guys, take a look, examine it. What functional groups do you see here? Yes, Rachel said alcohol, and that is also correct. So what gave it away that it was an alcohol? So you say the beginning. Can you give me a number? Can you tell me what wave number you mean? All right, from around 3,500. Yep, pretty good. Yep. You can give me a range. You can say, between 32 to 35, between 33 and 35. It doesn't have to be exact, as long as I can pinpoint the region, right? Just around the block, some people would say when giving directions. Like, yeah, between 3,500-ish, a little bit less. You see this OH stretch right here. Exactly. This is the OH stretch. Also kind of smooth, right? Kind of smooth. It's at around 30, so I would say definitely strong. Kind of broad, but not as broad as the wizard's beard. This is only about, I would say, 300 wave numbers wide. What are these peaks right here? What's this one? These really sharp ones. What are these right here? Yep, exactly. These are the CH stretches. Do we know if it's SP3, SP2? Actually, no, we don't, because we don't have any structural information. All we see is the signal. So, I mean, they're kind of sharp, so maybe it could be an aromatic ring, but for now, we don't know. What else? Do we see anything else significant? Anything we might be able to say, that looks suspicious, that looks like a signal? What about this here? If that was something, what could it be? Kind of a weak, sharp peak. It's somewhere in the double bond ranges between 1400 and 1800. This is where you would usually find double bonds. So what kind of double bond? Yes, right? Yes, Isaiah. The carbon-carbon double bond right there. So this is about 80%, I would say, right? It's also possible that it's not. So I would say, well, that kind of looks like a carbon-carbon double bond. And then my lab partner might say, well, I wasn't trying to make anything with a double bond. Oh, okay. Well, either you accidentally made something with a double bond or I'm reading the spectra incorrectly, right? There's always two possibilities. So in this case, we kind of stick to what we can claim. We definitely know there is an OH. There might be a carbon-carbon double bond, but we don't know, right? So, we will discuss it, but we wouldn't really report it. I wouldn't really make the claim. And yeah, and that's all we can know. That's all we can know about this. We need a formula, we need to take NMR, we need to take melting point, something else to determine what else the molecule could be. But this is all we can learn from the spectra. All right. So next example. How about this one? So maybe instead of seeing what we have, sometimes we can see what we don't have as well. So for example, let's say that we're looking at this and we're like, I don't really know. Okay, well, what don't you have? For example, if I go to 1700, do I see any carbonyls here? What would you say? Yes or no? Are there any carbonyls at 1700? Andres says no. Rachel says no. Yes, there is none. You are correct. Yes, their answer is no. There are no carbonyls. If there was a carbonyl, you would see a very strong, somewhat sharp signal that would be here at 1700. And since you don't have a carbonyl, you cannot have a carboxylic acid. You cannot have an ester. You cannot have, what else? An amide. Notice amide, right? You cannot have, what else? Just a ketone, etc., etc., right? So eliminating the carbonyl eliminates half of the list. So there's only a few more options left. So what else do we see? What else stands out? What are these peaks here? This set of peaks at 3000. We always see this, right? This is our CH stretch. So again, everything has CH stretches. I kind of see a few more signals. So for now, I'm going to ignore it and move on to the next one. What about here? What does that look like? It's between 3200 and 3500, so very strong, maybe a polar bond. Not very strong signal, however. So maybe not very electronegative, but still. Ruben says, is it an OH? Well, it could be. It's in the right region for sure, right? Let's take a look at our previous example for the OH and see if we find a right there, right? We said this was an OH, but look at the difference in the two signals. You see? So one of the things that we see is the intensity is significantly lower in the second example. And so that means that the bond is not as polar. So yes, it's polar, but it's less polar than OH. So what is less polar than an OH bond? NH, right? NH is less polar, but it's still polar. So it would give us a weaker intensity. And there's two peaks. So what does that tell us? What is the final conclusion? Is it a nitrogen carbon? Is it a nitrogen hydrogen? Is it a nitrogen hydrogen 2? Or is it not an NH at all? And move on till I get an answer. So you're not sure, is what you're telling me. Well, if we look at our previous example, right, where we said it was an OH, you see the signal's a lot stronger, right? You guys see that? Yep. NH2. We saw NH2, right? But look at the signal. It's stronger. This signal is an OH signal. And then look at the next signal. It's a lot weaker. So they both have the same range, but one is a lot stronger because OH is way more polar. It vibrates a lot more intensely with its dipole. So that's one of the first things you can use to distinguish between the OH and the NH. And then you see there's two peaks. You notice that for OH, it's usually a broad, smooth peak. See how this one is smooth? And you see this next one, it's just a little bit pointier. So the fact that you see the two peaks, that tells you that it would be NH, but more specifically, like you guys said in the chat. Yep, Zena and Adriana, yes, NH2, exactly. So this is an NH2 right here. And you have to tell me that, NH2. So we have an NH2. We don't have any carboxylic acids, esters, amides, ketones. We have our standard CH stretches. That's it. We cannot know anything else. Alrighty. So next example. How about this one? You guys tell me. Alrighty, and Rachel asks, is it one NH stretch and a CH stretch? And the answer is yes, you are correct. There is an NH stretch and a CH stretch, for sure. So the NH stretch is where? Give me the wave number. Yep, between 33 and 3500, exactly. So right here, this one. Again, it's not very smooth, it's not very strong, and there's one peak that kind of stands out. So this tells me this is an NH. And there's only one, so it's only NH. Probably connected to some carbon somewhere. And that's it. And then, of course, like Rachel said, we have our CH peaks right here. CH stretches. Always present. They're always going to be there. Doesn't really tell us anything. And some people might say, well, I have this peak here that's kind of strong. Maybe I would say medium at around 1100, right? Some would say, well, that's a carbon oxygen peak. Yes, but we don't know for sure. In this case, we also have carbon nitrogen. So this could also possibly be the carbon nitrogen peak. We don't know, right? Could also be this one. We don't really know, right? Could even be this one. We don't really know. Good guess. That would be a good like, oh, I'm trying to see if this makes any sense. Yes, yes, that would be a good guess as well. But again, the confidence for that would be a lot lower, so I probably wouldn't even like, you know, not gonna put him on my lab report or something. I would only really say the NH stretch for sure. And that's all we can learn. So, any questions so far? Is this kind of making more sense? Like the logic, how do you attack these problems? What do you ask yourself? If you always look for the carbonyl and it's not there, that's already a big step forward, I would say. So, all right. Let's see. Yep, and then here's another example. This one should be a little more familiar to you now. What functional groups are there for sure? And Rachel asked, if we put one of those where we couldn't tell on the lab report, would it be marked wrong? No, you would only get marked wrong on stuff that's like, for example, like if you call an OH like a CH, then yeah, that's wrong, right? Or if you point to like something that's not a carbonyl at like 1000 when carbonyls are at 1700, then yeah, that's wrong, right? But like if you point to a peak and you're like, oh, this could be a carbon oxygen peak and it's at 700, it's like, well, good guess, but no. Try to stick to the ones that we can tell like for sure. That's really what we go for when we're doing IR spectra, right? We only start guessing at the very end if we got nothing else. So yeah, good question. So for example, here, one thing stands out right away. So what's the first thing you would go to when you see this? CH, okay. And where's the CH at? So definitely CH. Ruben is saying OH, Rachel is saying OH, right? Both of these are here. Exactly. So give me the wave numbers. You guys are telling me what they are, but now you gotta tell me where. Where's the OH? Where's the CH? So Andrea said CH is at around 3000. Yep. This right here are the CH stretches. Where's the OH? Right? Zena and Rachel said 3500 to 3200. Yep. Yeah, plus minus a few. Yep. But it's in the region, right? This is your OH right here. See, it's smooth, it's strong, medium, broad range, right? Exactly. Good words, good descriptor words. Anything else? Do we see anything else that probably stands out? At this point, you're like, well, maybe not, right? And yeah, maybe not. If I had to guess, I would say maybe this one here and maybe this one here. This one's a little sharp, so possibly it could be a carbon-carbon double bond because it's in the region, it's sharp, kind of medium. This one could be a carbon oxygen. I mean, it's likely since we have an OH, I could say that it's a carbon oxygen like OH. But if I have some other element in here, it could also be like carbon nitrogen, right? Or carbon fluorine, or if I have one, I don't know. So this is why these peaks, you kind of look at them at the end. You're like, yeah, they're there, maybe. But at this point, we would need the information. We would need like the formula. We would need like a picture of the structure. It comes a little more difficult to guess that with certainty. The OH, I mean, that's distinct. That's why we focus on it. So again, this isn't 100% definitive. You don't have to look at all of the peaks. Just find the ones you're familiar with. But the more peaks you're familiar with, the better you get at doing this, right? So it also helps. Yep. Alrighty. How about this one? We haven't seen this one in a bit. I do notice it's very sharp. And remember, if you're not sure where to start, ask yourself, is there a carbonyl? So here's 1500, 16, here's 1700. Is there any carbonyl peak? 1700. No, right? If there were, you would see that it would look like this. It would be very strong and it would go all the way to the bottom and it would be kind of sharp. And we don't see it. So there's no carbonyl, there's no carboxylic acid, there's no amide, there's no blah, 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 right? Do we see an OH over here, like a kind of strong, kind of smooth OH over here in the region we expected, right? We don't see an OH either. We don't see an NH. Otherwise, it would look something like this, right? We don't see it either. So we're not seeing much of anything. So what do you think it is? What could it be? That also gives us information. So this is where we would pay attention to our CH peaks, our CH stretches. Take a look at this one right here. That one is a little stronger than the rest, and it's sharp. So it's a little bit stronger than the rest. What's a little stronger than a regular CH? Remember this one? This would be your sp2. That's right, sp2CH stretch right here. And at this point, you look for it because there's nothing else. There's no OH, there's no NH, there's no wizard's beard, there's no carbonyl. So you start looking at the CHs. At this point, you can start paying attention to them. And you'll notice, yeah, actually, I do see this peak a little bit to the left. This is going to be my sp2CH. And if you have an sp2CH, you also have a carbon-carbon double bond for sure. And that would be this peak right there. A little bit above 1500 or so. That one. And you can only say this for sure now because you've confirmed the sp2CH over here at around 3100. This one right here. So since you've confirmed that one, now you can point to this one and say, oh, well, obviously I have to have a carbon-carbon double bond somewhere. And that's why you can say that peak now for sure is carbon-carbon double bond. So any questions about this one? And also, since it's a little sharper than usual, I was gonna say there's also an aromatic ring here somewhere too. And that takes care of my carbon-carbon double bond, and that takes care of this sp2CH as well. So it is a possibility. Definitely for sure. So see, now you have two pieces of evidence. Now you can start putting it together and be like, oh, well, a benzene ring contains this and it's a little sharp. So now you can start making better guesses. You can start seeing the little details. Alrighty. Alrighty. So I want to show you one more website. I'm going to stop sharing real quick. One more website that you guys should definitely know. And it has been helping people and it continues to help people. So I show it. Alrighty. Alrighty. So this is the AIST spectral database for organic compounds. So you can Google it, click it, and you're gonna come to this website right here. It's like a terms and conditions agreement. Just go and scroll down and say, I agree. And this is an academic database. This is where I'm going to get some spectra for your quiz. I come here and I look up the names of some common compounds that we may have worked with, perhaps. And I find their spectra, and then I ask you questions about it. So for example, we work with acetone a lot, right? So I'm going to type in acetone, and I'm going to click search, and you see all of these results come back. And here it says IR. Now you know that IR means infrared spectroscopy, right? IR spectroscopy. And then here where it says acetone, it says Y. That means yes, there is an IR spectra for acetone. Go ahead and click it. And you'll see the spectra come up right there, right? You have the compound name, you have the formula, you have the molar mass. You can look for other stuff as well if you'd like regarding acetone. But we're doing IR, so I'm showing you the IR. And you see the structure down here at the bottom right, and you see the spectra, and you see the numbers. These are the X and the Y axes right here. So now you have the information. Somebody actually did this experiment and they measured this and they published it, and now you can use it for your research. This is an official academic source. You can use this for the rest of your academic lives. All right? And so you tell me then, what signals am I looking for? I have my structure here, right? What functional groups are in my structure? What are the peaks that you see in the spectrum? So I see carboxylic acid and C double bonded to OH stretch. Alrighty. So both of them have the carbonyl, right? The C double bonded O, which would be in a carboxylic acid, is definitely at 1700, right? So 1700 wave numbers, you see this peak. And if you look at the table, you see it's actually 1715 because you can see the number 4. It's very close to the 0 of the y-axis, right? So that would be that peak right there. That is this one right here. That is your carbonyl, right? But you'll notice there is no carboxylic acid in this compound. It's acetone. It's just a ketone, right? A carboxylic acid looks like this. A carboxylic acid looks like this compound right here, OH. And there is no OH in our structure. There's only carbonyl. You see? And so, yeah, that's a very common thing that happens. Make sure that the stuff that is in your structure, that will tell you what peaks to expect, right? Sometimes people say carbon fluorine and the structure doesn't have a fluorine at all. Well, you got to have it in the structure if you're going to see it in the IR spectra. So that's one of your clues you can use as well, especially if you're given the structure. You can use the structure to help you figure out what you expect to see. So here at 1700, we do see the carbonyl, for sure. And then what else are we expecting to see? There's nothing really else, right? There's just a CH3. So maybe these right here are your CH3s, right? So there is a little more going on here, but I'll let you guys think about that for the next few weeks. And then I might ask you a question about some other peaks that are showing up here. But this is an example, right? This is to show you I can go online, find the IR spectra, and practice. I can Google acetaminophen, I can Google ibuprofen, I can look for these compounds that I've actually used and learn some information about their structure based on what I've learned from IR. So this is just one example for how to do that. Let's do one more for here. So let's see. Let's do, I don't know, which one have we been working with recently? I think we did acetaminophen, right? Hmm. Let's do aspirin. I don't think I've done aspirin yet. Alrighty. So there's two types of aspirin. This is the actual name. So again, you can just Google it and look for the actual IUPAC name. So whichever one that you're looking for, the IR spectra will show up. So I think the one we're looking for is the ortho one. So here we go. And so again, you see down here, bottom right, you see the structure. So what functional groups do you see? Like just in the structure already, what do you see? C double bond O, right? So what is that called? What's the name of that bond? A C double bond O. What's it called? And also, what's the wave number? Where do you see it? There's a lot of peaks. You got to tell me. 1750 to 1850. Yep, that's a big range right there, right? So 1750 would be somewhere here, and then 1850 would be like over here somewhere. Yeah, big range. Well, it's definitely in the 1700s plus minus, but there's this one, there's this one, there's this one, there's this one, right? So which one is it, right? You're saying anhydride. Well, this looks like an ester compound here, and this one looks like a carboxylic acid. So anhydrides, they look similar, but they have their own structure as well. So that's a very good guess for sure. But we can see from here directly that it's ester and carboxylic acid, and both of them have carbonyls, right? So both of them have carbonyls. So those are the peaks that we start with. We look for the carbonyl peaks right here in the green. This one and this one. So we know carbonyls are roughly at 1700, like you said, right? 1750 to 1850. They're in that region. So let's look it up. Let's see, 15, 16, 17. So right here maybe and right here. And look, I see these two peaks and there's two carbonyls. So one of these carbonyls and then this one here is also a carbonyl. And I can say that we have two carbonyl peaks because the structure has two carbonyl peaks, you see? So now I can make these claims. Now I can actually say both of these are behaving as predicted, and the structure reflects that both of these are the signals. Does that make sense? So a question that I might ask you on a quiz might be, okay, there's two carbonyl peaks. Show me where they're at, and tell me which one is the top carbonyl and which one is the bottom carbonyl. Something about them lowers their wave number. And that's where you would have to sit down and think, oh, okay, what causes wave number to go down? And so now you can tell me which one is the top one and which one is the bottom one. So yeah, you can make these kinds of predictions once you understand the stuff that we talked about earlier. What else do we see? We saw the carbonyls. There's other groups here. Look at the structure. What other groups do we see? CH stretch, where is that at? Definitely CH stretch, but what's the numbers? 32 to 25. So 25 would be right here, yep, and 32 would be roughly, I would say over here, yep. So yep, these are the CH stretches, yes. These are also some CH stretches happening in there somewhere. Which ones? I can't say for sure, but they're in the region and they behave similarly, and it could be from the ring, or it could be these over here at the very end. One of these is behaving a little strange over here somewhere, right? But I don't know. At this point, I'm just starting to, think about how the structure relates to the signals. What else? I see this OH right here. There should be an OH signal. Well, it's what kind of OH? What kind of hydroxide is this? A bit hard to see with all the colors I put around it. But what kind of OH is that down here? I'm gonna use blue. This one. What kind of OH is this? What's the name of the functional group that it's this whole thing? What's the name of this whole thing? It's a type of acid of some sort. Contains carbonyls and hydroxides. What's it called? Carbonyl plus hydroxide. A carboxylic acid. That's right. It's a carboxylic acid hydroxide. And so carboxylic acids, we looked for that wizard's beard, and it doesn't look like the previous examples very much, but if you look at the width of the signal, right? It starts over here at around 24 and it goes to around 32. That's a pretty wide signal. And it's in the structure. You see there's a carboxylic acid in the structure. So now you can justify, you can say, hey, this is a wide signal, just like you would expect from the wizard's beard. Yeah, it doesn't look like a very well kept wizard, right? This guy's probably living in the forest and hasn't seen society in 20 years. But regardless, right? Regardless, it has the characteristics and it's in the structure. So we can say, this is my OH stretch for my carboxylic acid. This is my carboxylic OH right there. Does that make sense? And so these are the kinds of questions you might receive. You might be like, hey, here's the structure. Show me the peaks for what's in the structure. Or the other way around. Here's the peaks. Draw the structure. Make sense? So that's pretty much it in terms of the website. Again, it's the spectral database for the organic compounds. Make sure that you guys use this. I have people in 223B right now using it for NMR. So this is a good website to keep track of. This is a good website to use for practice and stuff of the sort. So let's show you the information you're going to receive for the final exam. So these PowerPoint slides, you can find them in the modules. So make sure you go back and practice on your own. You can ask me questions. But this right here, this is what you're getting for your final exam. And some people have told me that the information is not complete. So I would recommend studying as much as you can. And then again, if you commit some things to memory, it'll help you during the exam as well. But this is what you're getting. So hopefully this should be enough as well to help you with that. So are there any questions about any of the concepts or any of the topics that we discussed regarding IR, how we do it, what it's for? Alrighty. Well, that is the end of the lecture. Thank you very much for your attention. Really appreciate you being here. Let me know if you have any questions about anything. You can always email me. And next week, we will continue on in person as usual. We will start Lab 5, pre-lab quiz and the pre-lab procedures. So I will see you guys next Monday, and I'll stick around if you guys have any questions. So thank you very much for your attention, and we'll see you next week as well.